We're Space Exploration Alberta Robotics from the University of Alberta. I'm Indy, the president of the club, and this is our submission for SAR for URC 2025. This is our rover, KIP.
Hi, I'm William. On the mechanical team, we have been working on making the rover stronger, more reliable, and easier to control. We have been focused on refining the robotic arm, installing new motors, reinforcing key parts, and making sure everything fits together well with the rest of the rover. To keep the arm strong but lightweight, we use carbon fiber tubes for the main structure. We also forged carbon fiber for the housings of the gearboxes to make them tough but light. The link flanges were 3D printed using carbon nylon, giving us a good mix of strength and flexibility. Now that we have installed the new motors, the arm has better torque and precision, which helps it move more smoothly. We have also worked on reducing backlash, so it's more accurate. At the same time, we have made the end effector stronger, so it can handle more stress without wearing out. Right now, we are working on the mounts for the steering system to improve control and movement. We're going to keep refining these systems to make sure everything runs smoothly and efficiently so the rover is as reliable as possible.
For our electrical team, we've been mainly working on improving our motor control boards and our battery system. Battery system has been completely replaced since last year. We're now using a singular 700 watt-hour LiPo battery instead of multiple smaller ones in parallel, which allows us to shrink the battery management system size while providing overall more energy. We can run the rover for the required 1 hour and more if we operate the rover conservatively. This new battery system is encapsulated as a modular device to be used for the rover and all future endeavors. For the motor control system, we are using our multi-purpose motor control boards from last year. We have been working on the embedded programming to better leverage the power of our motor boards to improve the energy efficiencies and improve motor control feedback for the software team. And throughout all of this, we've been keeping our systems accessible and repairable so that we'll be ready for anything during competition.
Our 6 degrees of freedom robotic arm leverages inverse kinematics for real-time servo actuation. This system supports both teleoperation and autonomous navigation to predefined waypoints, ensuring adaptability in complex tasks such as tool manipulation and autonomous typing a launch key. The integration of inverse kinematics ensures an efficient computation of joint angles, allowing the arm to dynamically adjust to environmental constraints. Combined with robust feedback mechanisms, this design enhances operational accuracy and reliability, making it a critical component for mission success in the URC competition.
At its core, we utilize NAV2, which is a ROS2 navigation stack to enable real-time path planning and obstacle avoidance. This allows the rover to autonomously navigate through various terrains while dynamically adjusting to changes in its environment. For precise localization, we've fused point cloud data from a stereo camera using SLAM and location data from a GPS sensor. The camera also provides visual odometry, enhancing the odometry from the wheels and IMU. To interact with sample objects or tools, the rover employs object detection algorithms using the stereo camera. This allows for precise identification and localization of targets, enabling autonomous manipulation and retrieval tasks. To accomplish our mission tasks, we utilize a behavior tree along with the localization and object detection algorithms in order to break the tasks into smaller pieces that the robot can complete in a structured order.
To complete the science objectives, our team has developed a collection, testing, and caching system. An auger was designed to dig to a depth of 10 centimeters, take temperature and moisture readings at that depth, and bring up soil to be tested and stored. The wiring for the probes runs through the center of the auger to take readings, and they are digitally read by the onboard system. As the auger rotates and digs downwards, the soil climbs upwards and then is deposited into a funnel, where it is then tested using vacuum filtration. Deionized water is deposited into the soil, and a vacuum pump is used to pull it downward through the soil. The solution is passed through a filter and reacts with the testing strips in the channel. This year, we have made the channel with the testing strips horizontal to conserve space and improve recording of results. The channel is well sealed with adhesives and acrylic film in front of the test strip, so the results can be visually detected by an onboard camera, as the colors change to reveal protein and nutrient content. The water is kept securely inside the base of the vacuum filtration system and can be disposed of later. At the conclusion of the first test, the auger rotates to direct the collected soil into another testing chamber for the second sampling site. For the cache sample, the auger rotates to deposit into a third container, which is rotated by a stepper motor to be sealed. This can be easily removed for examination. This system has been greatly improved over last year by developing an auger system rather than relying on the arm to scoop soil, allowing us to have accurate readings of what depth we're getting the soil from and to dig deeper. We've added probes to the center of the auger, which can test for temperature and moisture at a depth. We've also made modifications to the testing system and improved the caching apparatus.
Thank you for watching our video, and to our entire team that has been working on this rover for the past year.